Let me maximize the screen. All right, so good afternoon, everyone. Um, and welcome back to our lecture episode. Today, I shall be talking about the introduction to the moon, part one. This is going to be the first part of several parts that I will be teaching about the moon. I'll be discussing several topics about the moon in subsequent sections. So in the table of content, I'll be talking about what is the moon, some basic facts about the moon, the moon's formation and evolution, the moon's surface and features. And then others will continue other day, maybe next week. So understanding the moon, so the Earth's celestial companion. But before talk about that, what is the moon? Okay, what is a moon? What is a moon? So a moon simply means a celestial body called a natural satellite that orbits a planet or a dwarf planet. So any natural object that is orbiting a planet or a dwarf planet is defined as a moon. So no matter the size, it could be the size of a car, it could be the size of even of moon itself or moon itself. So anything that is orbiting another celestial object or a planet or a dwarf planet is defined as a moon. Now, how about our own moon? Our own moon is called the moon with capital letter M. So our moon is our only natural satellite. Earth has only one moon, and it is regarded as our closest neighbor in the universe. The moon is our closest neighbor in the universe, so it is very important for us to understand it. Then it is the second brightest object in the sky. The moon is the second brightest object in the sky. The brightest object in the sky is the sun. Then we have the moon. Then we have the International Space Station, and the list goes on and on. So the moon is the fifth largest moon in the solar system. Remember that other planets also have their own moons, okay? Starting from Earth to Mars to Saturn to Jupiter and so on, all have the moon. Some of them have more than one moons. So if you add all of them together, they should give you around 290. Okay. Now, out of that 290, and I'm telling you right now that Earth is just fifth largest. So it means others can be very small. And in terms of relative size to the host planets, our moon is the largest of all of them relative to the host planets. So that is some basic facts about the moon. Sorry, that's like some definitions about the moon. So I'm going to talk about some basic facts about the moon in terms of the size of the moon, the orbit of the moon, the Earth-Moon distance, orbital period, tidal effects, and elliptical inclination. So now, the moon orbits the Earth just like the Earth orbits the sun. And that orbit is elliptical. It's an elliptical orbit, not circular, okay? It is not a perfect circle. Now, for elliptical shapes, elliptical path, it has two foci, and the Earth happens to be in one of those foci. Okay, so here is the Earth, one of the foci. Here's another foci. So as the moon orbits the Earth in this elliptical orbit, there are some points around the orbit where it is closer to Earth. Okay, we call that perigee, and there are points where it's farthest away from Earth. We call that apogee. Now, at perigee, the distance to the moon is around 363,300 kilometers. Okay, so at this distance, the moon appears slightly larger than it used to be before. Sometimes when you look at the moon, it appears slightly larger. It is not because something is wrong with it, but because it is closer. Okay, then at apogee, the moon is further out, and the distance is around 405,500 kilometers. So at this point, the moon appears slightly smaller. So the reason why it appears slightly larger and smaller throughout the year is because of the elliptical orbit. If the orbit were to be a perfect circle, the moon remains the same size throughout the year. That is the basic fact. So here is the shape of the moon where it is at perigee, that is closest approach, and where is at apogee and further out. So the distance to the moon. Now, if you take these two distances that I just mentioned here, if you add them together and divide them by 2, that will give you an average distance of about 384,400 kilometers. So that is the average distance to the moon. Okay. So now, do you know that all the planets in our solar system, starting from Mercury to Saturn, sorry, from Mercury to Venus, Neptune, sorry, from Mercury to Neptune, those are the only planets we recognize. If you start all of them diameter from meaning from one pole to the other, their distance can fit in between the distance of Earth and the moon. So the reason I'm saying this is because I want to emphasize that the moon is really farther out. The moon is really, really far away. Sometimes we do not know this. The moon is really, really far away. So, but it is not going to perfectly fit in, okay? Because this average distance that I mentioned here is not a real distance to the moon, okay? It is just an average. So if you want to align them perfectly in between, if you want to align the planet perfectly between the moon and Earth, you have to wait at apogee, because at apogee is when it is further out, and that distance corresponds to about 405,500 kilometers. If you fit it in when it's at perigee, they can't fit it, because if you add all the diameters, if you add all of that together, they are going to give you a distance about 392,766 kilometers. So that's what I'm saying. So the moon can fit at apogee. That is when it's further out. So how about the orbital period? The moon completes one revolution around Earth once every month. Okay. Now there are two methods of measurements. Okay, there are two methods of measurement. We have the sidereal month, which is about 27.3 days. So this time is what it takes it for the moon to make one complete revolution. That is 360 degrees around the Earth. So, and this is measured relative to the background stars. Okay, it is measured relative to the background stars. Then we have the synodic month. The synodic month consists of the sidereal month, which is 27.3 days, plus additional 2.2 days for the moon to move back to its new moon phase, new moon position. So the one we use is the synodic month, the one we call 1 month, because 1 month is on the average 30 days. So, but the real number is 29.5. So we are using an approximate date. We are using an approximate date. So humanity most frequently uses the synodic months. So why do we only see one side of the moon? And the reason why we see one side of the reason why one face of the moon is facing us is because of tidal effect. This tidal effect, the science, the physics behind tidal effect is very complicated, but I'm going to simplify it for you. Billions of years ago, after the formation of the moon from the debris, I'm going to explain that better. A day on Earth compared to a day now, billions of years ago, a day on Earth lasted from between 10 to 12 hours. Remember, today, one day is 24 hours, but then it was 10 to 12 hours. But a day on the moon was 25 Earth days, but today it is about 29.5 days. That is 1 month. Okay, so it means that they were back in those days, billions of years ago, they were spinning faster. They were spinning much faster than what they are today. And they were much closer. They were much closer and spinning faster. But here is what tidal effect does. So the closer the moon exerted tidal forces, accelerating the transfer of angular momentum, which slowed Earth's rotation and pushed the moon outwards. So this gradually lengthened the orbital period over time. So the moon was, there was like a transfer of angular momentum from Earth to the moon. So that pushed the moon further out. So even today, it is still happening. Even today, it is happening. Every year, it is estimated that the moon moves away from Earth at a distance of about 3.8 centimeters per year. 3.8 centimeters per year. If you want to understand the significance of this, you can multiply 3.8 centimeters by your age. If you are 30 years or 40 years, if you multiply that, you see how farther out the moon has shifted away from Earth since you were born. So it is a very, very, very significant factor. And we're going to revisit that when we talk about eclipses, because in the future, we may not have eclipses anymore, at least total eclipses, because of this recession. So tidal locking is a gravitational phenomenon that occurs between two astronomical bodies, like a planet and its moon, by transferring spin angular momentum from one to another. So tidal locking, it is not only unique, to our planet and the moon. It is also experienced by other celestial bodies. Okay, so when an object is tidally locked, the time it takes to rotate around its axis is the same as the time it takes to orbit around its partner. Okay, so this results in one face of the object always facing the partner. So a well-known example of this is our moon, like we have always seen. So it is rotating at the same rate at which it is revolving around the Earth. So that is why we always see one side of the moon always facing Earth. It is actually spinning, but we can only see one face facing us. Another example is Jupiter's moon called Leo, Europa, and Ganymede. They are tidally locked to Jupiter. Even the moons of Saturn, some moons of Saturn and Uranus and Neptune are also tidally locked. And if we extend it to other solar systems, even exoplanets, some planets are tidally locked to their host stars, like the hot Jupiters. That is why they are always very hot, because one side is always being hit by the radiation from the host star. So tidal locking is not only significant, it's not only seen between Earth and the moon, it is also seen in the universe. In fact, every object that is orbiting another is tending towards tidal locking. So here is a simulation to demonstrate the tidal locking of between the Earth and the moon. So you can see that the moon is orbiting and also spinning around the Earth, but only one face is facing the Earth. Let me play it again. Only one face is facing Earth. So this is just a demonstration of the process. So now, in terms of orbital inclination, the moon's orbit is tilted at an angle of 5.1 degrees relative to the Earth's orbital plane or orbit around the sun. So this is why we don't get to see eclipses every month, because in the whole sense of it, we are supposed to be seeing eclipses, but we don't. I mean, every month we're supposed to be seeing eclipses, but because of this reason, we don't get to see eclipses. I'm going to explain that much later. So here is the orbital plane of the Earth. So this blue line is the orbital plane of the Earth, and here is the orbital plane of the moon. So here is for Earth, here is for the moon. So the point of intersection makes an angle of 5.1 degrees. And that is the single reason why we don't experience eclipses. Assuming that there was no inclination, maybe the inclination is zero, we might receive eclipses every month on our planet. So how about the moon's formation and evolution? Let's talk about the moon's formation, how the moon was formed. Around 4.5 billion years ago, think about that, 4.5 billion years ago, during the early formation of the solar system, there was a Mars-sized body called the Theia. It collided with the with Earth, head-on collision in a very catastrophic impact. So the collision ejected enormous amounts of molten rock and debris into space. Okay, so over time, this debris coalesced due to gravity, and that led to the formation of the moon. And I'm going to show you that using a simulation. So here is the Earth, and that is that ancient Mars-sized object. So you can see how it collided with Earth and it got shattered. Even some materials of Earth were spewed up into space. And here you can see the moon forming. So the moon formed from the debris from the incident. Let me play that again so that you can see it well. So it collides with Earth, and then the debris, the whole thing converted to a molten form, and from that the moon formed. So that is how the moon formed from the debris. So now let us talk about the changes after the formation of the moon. So the moon experienced intense after the formation, okay, it started to cool down. Now, in that process of cooling down, it experienced intense meteorite impact. So during a period called the late heavy bombardment period, okay? So craters or basins, okay, we are formed, large craters, and that is where the South Pole Belt Basin came about, okay? I'll explain that later. But some impact caused lava to erupt from the interior. In the same way, if you got shot by a bullet, okay, the bullet penetrates you and your blood comes out. So some of these debris caused lava to erupt from the interior. So, and this lava, they filled the craters, forming what we call the Luna Maria, the dark plains we can see. When you look at the moon, the picture of the moon, those dark plains you can see, they're called the Luna Maria. Okay. So here is our simulation. That is a simulation of what happened during the early times after the formation. Okay, this is the evolution of the moon now. So you're gonna watch the video. So here is the moon. It is cooling down. It is cooling down after the formation. Okay, it is cooling down. Okay, and the surface is very smooth. And then you have this giant impact here. This formed the Icon Belt, very giant impact. And as that is cooling too, other asteroid and meteorite rain down on it, exposing the interior. So that is exactly what happened. It got heavily bombarded by this heavy objects. And then you have those dark plains now. You're gonna see those dark plains, the Luna Maria. Luna Maria, I'm gonna see the dark plains. So you see the dark plains forming. So this is as a result of the heavy bombardment that made the interior, the lava inside to come out on the surface. So you now have these two distinct surfaces. You have the dark plains and the white plains. So we call this Luna Maria, or we call it the highlands. I'm going to explain those in the future. I'm going to explain those in the future. So this is the evolution of the moon. So Now, the current feature of the moon is covered in fine dusty material called re regolith, created by billions of years of meteorite impacts, okay? It still has impact craters forming due to occasional asteroid collisions, right? Then, then there is water ice, not water, liquid water, but in the ice, in the solid form. It has been detected in permanently shadowed craters at the poles of the moon. So they offer potential resources for future lunar missions. So here is the surface of the moon. So we're going to be discussing the surface of the moon, okay, and its features. But before I do that, I want you to understand that the moon surface is divided into two distinct types of terrain. So we have the mare. Mare is the singular form of Maria, and then we have the highlands. Okay, the highlands is terra in Latin. So that Maria is a Latin word. Okay, it means sea because in the ancient civilization, they thought when they looked at the moon, they thought they were water, like sea, like we have it on Earth. So they thought it was water, so they call it Maria. So the name stuck. So we call it Lunar Maria. But the singular is Mare, so don't get confused between these and the Maria. Then we also have the impact crater, we have the lunar ridges, the release and domes. So then we also have the lunar poles and water ice, the regoliths and the tectonic and seismic activities on the moon. These other three, I'm going to be talking about them in my next episode, but these other four, I'm going to be explaining them right now. So note, like Earth, the moon's surface is shaped by billions of years of asteroid impacts, volcanic activities, and extreme environmental conditions, okay? But unlike Earth, the moon lacks an atmosphere. It lacks an atmosphere, liquid water, and it's significant weathering processes. Remember, for Earth, if an asteroid falls on Earth, maybe a small asteroid, it can burn up in the atmosphere. Or even if it lands at all on the surface, and maybe it creates a crater, with time, the crater might be covered up due to wind. Wind is going to blow up dust and sand, and water. Water is going to flow after rain to cover it up. So over time, after a very long time, we don't get to see craters created by asteroid impact on Earth. But that is different for the moon because the moon has no atmosphere, it has no liquid water. So any impact on the moon stays for millions of years or even billions of years. So this means that the surface has remained largely unchanged for millions of years. So let's talk about the lunar highlands, which is called the Terra. So the lunar highlands are the oldest part of the moon, dating back to over 4 billion years. 4 billion years. So these regions are light colored. They are looking white, okay? Heavily created and mostly composed of anorthosite. Anorthosite is a rock we use on Earth to make ceramics and glass. So the highlands were formed when the moon's surface first solidified from its magma ocean phase. So here is the highlands, the white areas. White areas is called the lunar highland. Some scientists have given it some names. Okay, we have the Montes Apenninus, we have the Montes Caucasus, we have Montes Carpathus, and many more. So you can decide to explore the names further. We have so many names for these different regions. These are the mountain areas of the moon, the mountainous areas of the moon. Then the Icon Belt, it is a basin which is, it is the largest and the deepest impact crater on the moon. So it is Icon Belt. You cannot see it from Earth. It is towards the far side of the moon. So you cannot see it even if you take a picture of the moon, unless you have a satellite that takes a picture from the other side, take the picture of the far side of the moon. So that is where you can see the Icon Belt. This is where you have the largest deposit of the crater of craters in the solar system. It is the biggest crater impact in the solar system or on any object in the solar system. So we call it the Icon Belt. It is located in the highlands sides of the moon. So how about the Luna Maria, the sea, the dark volcanic plains? So the Maria, Latin for sea, are large, flat plains formed by ancient volcanic activity. So these regions are darker in color because they consist of basalt. Okay, basalt are volcanic rocks rich in iron and magnesium. Okay, so they were generated after very large impacts penetrated the crust of our moon and excavated basins. During later volcanic episodes or eruptions, volcanic processes, liquid magma came to the surface and filled these basins. Then it cooled down and solidified. It formed the large flat areas we can still see today. So the Maria makes about 16% of the lunar surface. So, and you can see it, you can see it, you can see it when you look at lunar pictures. So they are mostly the places where astronauts land because they are solid surfaces. Okay, so most of the space probes that I hear about, I mean, manned missions like astronaut landing happen at those lunar Maria because they are solid surfaces. So here's the picture from a European satellite that shows the highlands in the lunar Maria. They are plains, they are just flat, smooth plains on the surface of the moon. So impact crater, the moon most common features. Okay. So since the moon lacks an atmosphere, meteors and asteroids impact the surface directly without burning up. This has created millions of impact craters of all sizes on the moon. So how is this crater formed? I want you to pay attention on the science behind lunar craters. I want you to pay attention. Craters form when an asteroid or meteoroid collide with the moon at a high speed of about 160,000 kilometers per hour. So at this such kinetic energy, the impact can generate immense heat and pressure, and they are enough to melt the surface, the direct surface they are touching, and they're going to melt it and inject debris in all directions. So over time, smaller impact and space weathering modify the crater appearance. So here is the picture demonstrating when it is falling to the surface. So here is the impact. So here, this is when it starts to melt and injecting the debris in all directions. And here is aftermath. So here are some notable pictures of lunar craters. So we have the Tycho. If you look at lunar pictures, you see the Tycho. It's a very, very prominent feature on the moon. So we call it the Tycho crater. It is a bright young impact crater, which is about 85 kilometers wide, with prominent ray systems formed about 108 million years ago. So we also have the we have the Copernicus crater, which is about 93 kilometers wide, okay, and well preserved crater. It's a well preserved crater. It is known as the queen of the moon because of its beauty. So here is more pictures. We have the Aristarchus crater. So one of the brightest lunar craters located near a region with evidence of past volcanic activities. And here is the Aiken belt. I used an AI generated image so that you can see the magnitude of this crater. It is the largest known impact crater in the solar system, spanning about 2,500 kilometers in diameter and nearly 8 kilometers deep. So we are done with that. Let's talk about lunar reliefs, ridges, domes, and lava tubes. Apart from the craters, the moon also has unique geological formations that hint at its volcanic and tectonic past. So let's talk about the lunar reliefs. The lunar reliefs are long, okay, narrow depressions or trenches on the moon's surface, okay, likely created by ancient lava flows or tectonic activity. So here are some pictures of the lunar reliefs. So these are just trenches created by the by by, by lava when doing those volcanic activity periods, not because of water, but because of lava. So here are some examples of the lunar release. There are long depressions of the moon. So here are other examples. So here are another examples. The missions, the lunar missions that landed astronauts to the moon were landed at the side. So here are different positions. So here is another example of a lunar release. Very beautiful. So there's another picture. If you observe the picture of the moon, you see how shadow is cast on the moon. It is usually very, very sharp. And the reason is because there's no atmosphere on the moon to scatter light. Okay. So the shadow is usually very sharp, very, very sharp. So we have the lunar ridges. The lunar ridges. So you can see the picture here. So they are long raised features, long raised. Remember, the ridges are like ridges are long raised. Ridges are long depressions. So know the difference. They are long raised features that look like wrinkles or ridges on the moon's surface, found mainly in Lunar Maria. Okay, they indicate the moon's volcanic history. So here is the long ridges, the moon. So we have the lunar domes. We have the dome. They are small shield volcanoes formed by slow, thick lava eruption. So here are the domes. Then, this is probably the most interesting part. Lunar lava tubes. They are potential future astronaut homes. So the lunar lava tubes are underground tunnels formed by ancient volcanic activity. They are one of the best potential locations for future astronauts' habitat because they provide natural protection from harsh lunar conditions. So these are an AI-generated image of lunar lava tubes. These are not real pictures. These are AI, but this is how big they are and how they are. So how are they formed? They are created by ancient lava flows from ancient volcanic eruption. So as the lava is flowing across the lunar surface, the outer layers they cool down, okay, and harden, while the inner lava kept moving, leaving behind a hollow tubes when drained. So here are more pictures of the lunar lava tubes. But here is the live picture, not AI. These are live pictures. We haven't really gotten an image of the inside, okay? So these are the outside with satellites, the lava tubes of the moon. So they are quite very big, quite very big. So the lava tubes can be very huge, okay? So maybe 100 meters wide, 100 meters wide, and stretch for tens of kilometers. They are much larger than Earth lava tube because the moon has lower gravity. So now, why should astronauts live in them? Why should astronauts live in them? First of all, the first reason is radiation, protection from radiation. You know, the moon has no atmosphere or magnetic field. These two protect us from meteorites, meteors, okay, and also cosmic rays. But on the moon has no atmosphere or magnetic field. So to be able to live without harm on the moon, astronauts are going to be exposed to these dangerous cosmic and solar radiations. So lava tubes act as a natural shield from these agents. So in terms of temperature, during the day on the moon, the side that is facing the moon, the temperature can be as high as about high as 127 degrees Celsius or 260 degrees Fahrenheit. Okay, in the nighttime when it is not facing the moon, it can be as cold as minus 173 degrees Celsius. Very, very cold. So lava tubes maintain a more stable temperature, so astronauts can live there, stay there, and get shielded. So how about meteorite shielding? The moon has no atmosphere, so small meteorites constantly hit the surface. So lava tubes provide natural cover from impact. Then lava tubes have they contain water ice. Okay, so it's essential for making oxygen. For water, through electrolysis, you can produce oxygen from water. Astronauts can also drink from that, and also they're going to use it for rocket fuels. It's a component for rocket fuels. So these are the reasons why astronauts would live in the lava tubes. So this is the end of my lecture. I'm going to continue on this part. Next week, I'll talk about introduction to the moon, part 2. I'll talk about other aspects of the moon. So thank you for paying attention, and you can ask a question in the comment section. Thank you.